You are buying one mango. It looks perfect. But until you cut it, you cannot know how sweet it will be. Suppose you had records from hundreds of mangoes that people already tasted. Could a machine use those experiences to guess the sweetness of this one before the knife touches it? Before we ask a machine, what would you do? Look at the color, smell it, weigh it, press it gently. Choose one clue now, and do not worry about being wrong. Your choice is the beginning of the model. Let us start with softness. Not because softness tells us everything. It clearly does not. We choose one clue so we can see the reasoning. For every mango in our old records, we know two numbers: how soft it felt and how sweet people rated it after tasting. A softness of 2 came with a sweetness near 3. A softness near 7 often came with a sweetness near 8. Now, a new mango arrives. Its softness is 6.3. What number should we predict? Our first idea is completely reasonable. Write a rule. If softness is below 5, predict 4. Otherwise, predict 8. It works for some mangoes. But look near the boundary. A mango at 4.9 gets 4. Another at 5.1 gets 8. Almost the same softness. Wildly different answers. The world changed gradually. Our rule jumped. We could avoid that jump by using the average sweetness of every mango we have tasted. That gives us one safe answer, about 6. It is a useful baseline, but it gives the same answer to a hard mango and a soft mango. The prediction is stable because it ignores the clue we measured. What if we find the old mango with the closest softness and copy its sweetness? That is not a foolish idea. In fact, it belongs to a real family of machine learning methods we will rediscover later. But with only one nearby example, a little noise can move the answer sharply. And between remembered mangoes, the prediction changes in steps. Can we use all the experience and still let the answer change smoothly? The table is hiding something. Put softness from low to high along the bottom. Put sweetness from low to high along the side. Each old mango becomes 1 point. Now the relationship is visible. The points do not form a perfect path. Real experience is noisy, but they lean upward. Softer mangoes in this small dataset are generally rated sweeter. Pose. We do not need to remember every point. We need one rule that follows the overall direction. A rule that can accept any softness value, even one we have never seen, and return a reasonable sweetness estimate. What is the simplest rule you could draw? A straight line is the simplest place to begin. Not because nature promises to be straight, and not because this line will touch every mango. The line summarizes a trend. Give it a new softness value. Move up to the line and read the predicted sweetness. One continuous rule has replaced a pile of separate memories. But there is a problem. I can draw this line, or this one, or this one. Every line makes a different prediction. Saying, draw a line through the middle sounds helpful, but it is not precise enough for a machine. We have invented the right kind of rule. We have not yet invented a fair way to choose its exact position. You already have the central idea. Now we can name it. Predicting a number is called regression. Using a straight line rule is linear regression. Linear describes the shape of the rule. Regression describes the kind of answer. A number, not a category. The equation is only our visual rule written precisely. Predicted sweetness equals bias plus weight times softness. We usually write that as y hat equals b plus wx. X is the softness we observe. W is the weight, the slope of the line, how much the prediction changes when softness increases by 1 unit. B is the bias, the vertical starting position of the line. And y hat means prediction. The hat matters. It reminds us that the number is an estimate, not the truth. For our candidate line, the bias is 1.8 and the weight is 0.82. The new mango has softness 6.3. 1.8 plus 0.82 times 6.3 gives 6.97. We would say about 7 out of 10. The machine's guess is simply the output of its learned rule. In code, the whole prediction fits inside one function. Multiply the input by the weight. Add the bias. Return the result. Increase the weight and the line tilts upward. Increase the bias and the whole line moves upward. Those two adjustable numbers are the model's parameters. Training will choose them. For now, changing them by hand lets us see exactly what the model is capable of expressing. Now let us break it. 2 mangoes can have almost the same softness and different sweetness. Variety, aroma, harvest maturity, and storage may all matter. Softness alone is not enough. A straight line also assumes the same amount of change across the whole range. And if we ask about a softness far beyond anything in our records, the line will still answer, even when experience gives it no reason to be confident. Prediction is not certainty. A pattern is not proof of cause. Which new problem has the same structure? Decide whether a mango is ripe. Predict how many minutes a delivery will take. Or group shoppers by behavior. Only one asks for a number from measured clues. Delivery time. The story changed. The structure did not. Inputs go in. A numerical estimate comes out. That is the regression pattern. We now know what kind of rule can make a numerical guess, but we still have many possible lines. Which one should the machine choose? To answer that, the machine needs a way to measure how wrong every guess is. In the next episode, we will invent that measurement ourselves. If this is how you want to learn AI, subscribe and join us. Like the video, so more curious minds can find the series. And tell us in the comments what clicked, what was unclear, and what we should improve. Your feedback will shape the episodes that follow.